So we saw that in stressing a buffer, if I add a little bit of strong acid or strong base, it does not change the pH as drastically as it would if I added that strong acid or strong base to an unbuffered pure water solution. But there is a limit. Now, a good buffer should be able to neutralize moderate amounts of added acid or base, but I can only add so much, right? So buffering range is the pH range at which the buffer can be effective. And so if I try to make something that's a carbonate buffer work at a pH of 10, right, I'm out of the buffer's range. And the buffering capacity is the amount of acid or base a buffer can neutralize, right? So this buffering range is going to be related to the ratio of the conjugate acid and conjugate base. It's how much can I shift it from the pKa value. And buffering capacity refers to how many moles of the conjugate acid or conjugate base I've got. And that's going to limit how many moles of strong acid or strong base that it can neutralize. Right? So it's going to depend on the relative amounts of the acids and base and the absolute concentrations, the numbers of moles of acids and base. So it's the ratio and how much. Right? A buffer is going to be most effective when it's within plus or minus, when the acid to base ratio is going to be between 0.1 and 10. So you only want, so if you've got like a 9 up here and 1 down here, you're probably okay. Like a 1-to-1 ratio, hunky-dory, great, right? It can neutralize both acids and bases, right? If you get something up here where I've got a lot of base, right, 10 times more base than acid, right, I can neutralize a lot of acid, but not a lot of base. And if I got a lot of base down here, and I get 10 times more acid than base, I can neutralize a lot more base, but if I try to add in a little bit of acid, it's not going to work. So, substituting into the Henderson-Hasselbalch equation, we can calculate the maximum and minimum pH at which the buffer will be effective. So pH is pKa plus the log of AHA. So the low range is going to be the pH plus pKa plus the log of 0.1, or minus pH equals pKa minus 1, and the high pH is going to be pH equals pKa plus the log of 10, or pH equals pKa plus 1. So therefore, the effective pH range of a buffer is going to be plus or minus 1 pH unit around the pKa. Okay? So if we want to make a buffer, we're going to choose one whose pKa value is closest to the pH of the buffer. Okay? Buffering capacity. And a concentrated buffer can neutralize more added acid or base than a dilute buffer. That's, you don't want to go around diluting buffers. These are both going to have the same pH because the ratio of H plus and A minus is the same. But this guy is going to be a tougher buffer to break than this guy, right? So they'll both have pH 7, for example, or pH 4.8, but this is going to be able to absorb greater changes. Right? It's a buffer. It can take bigger hits. Right? So the buffer will be most effective at neutralizing acids and bases when the acid to base ratio is 1. So a buffer will be effective in that 0.1 to 10 range. And the buffer will be most effective when the acid or base concentrations are large. Right? So our buffering capacity is how much can we add without causing that large change in pH. All right? In other words, when do we run out of the conjugate acid or conjugate base and our X's small approximation no longer holds? When have we completely neutralized one of the things? Right? So buffering capacity increases with increasing absolute concentration of the buffer components. If I've got a higher ionic strength buffer, I've got more stuff in my buffer, it's going to be able to absorb more strong acid or more base. As the ratio of conjugate acid to conjugate base approaches 1, the ability to neutralize both of the components improves, both acids or bases improves. Buffers that need to work mainly with added acid generally have more base than acid, and buffers that generally need to work with adding bases generally have more of the acid form than the base form, because the acid form is what's absorbing that added strong base. So, How do I prepare a buffer with specific pH? I can look at the concentration condition, right? That concentration condition says we want the ratio of acid to base to be within a 10 to 1 or 1 to 10 ratio. And we want our effective range to be plus or minus a pKa of 1. So I've got a variety of different weak acids, and they've got their unique Ka values, and they're going to have different pKa values. Right? So if I want a pH buffer to buffer something that's around 5, for example, right, I would pick something like this. Right, this is too high, and this guy's too low. If I wanted something that's going to buffer around 3, well, I could pick either one of these guys. Or if I wanted something that was a nice basic buffer around 9, I'd probably pick HCN here. And so, which one would I pick to have a buffer around 4.5? And so this is my target pH, is pH of 4.5. Right? I've got 3 possible candidates. Right? I've got this guy here. This looks like acetic acid and benzoic acid and maybe formic acid. Right? So of these, right, these are the ones that are anywhere close. The benzoic and the acetic are going to be the closest. Right, so we'll pick the acetic acid. Right. I know the pH is fixed because I said I wanted it at 4.5. I got the pKa is 4.19. Right, and then it's going to be the benzoic acid. The log. I want to adjust it by changing the relative concentrations of the conjugate base and the conjugate acid. All right, so I'm going to leave these guys. I'm going to move this 4.19 over to the other side and get 2.04 is equal to the ratio of conjugate base to conjugate acid. All right, so my 2.4 is the ratio of A to Ha. So I can dissolve 2.04 moles of sodium benzoate and 1 mole of benzoic acid in enough water to form a 1 liter of solution. If the solubility of these substances does not permit them to dissolve, you can reduce the amounts but change the ratio, right? So I could do, take this half the number of moles and this half the number of moles. It'll be the same ratio, and that means it'll still have the same pH. It won't be as strong a buffer. It won't be have the same buffering capacity, right? I could, for example, dissolve 0.0408 moles of sodium benzoate and 0.02 moles of benzoic acid to form a 1 liter solution. Right? Same pH, because the ratios are going to be the same here to here and here to here. Right? So this term would be the same, but the buffering capacity would be less. Right? So, which acid would you choose to combine with sodium salt to make a buffered solution at a pH of 4.25? For the best choice, calculate the ratio of the conjugate base to the acid required to attain the desired pH. Right, so I want 4.25. I've got chlorus, which is 1.95, nitrous, 3.34, formic, 3.74, hypochlorous, 7.52. I want something that's 4.25. This guy's out. It's a little too high. It's 2 pH units away. And this guy is within 1 pH unit. This guy is just barely within 1 pH unit. So we're going to go with the formic acid. And it's got the pKa that is closest. So my pH equals pKa plus the log of AHA. I start off with 4.25 is my given target pH. E is equal to 3.74. That's my equal position, my pKa, right? Plus the log of base to acid. Now this up here is more basic than the pKa, so I know I'm going to get a positive bigger than 1 number here, so the log of the base to the acid. All right, so I need to adjust this pH baseward. So it's going to be 4.25 minus 0.347 is equal to 0.51. So my base to acid ratio is 10 to the 0.051, so I get 3.24. Right, so I need 3.24 times more base than acid. Right? How much do I add in? Depends on how much this is going to dissolve. Sometimes they will tell you how to get out of the ratio. This setup leaves you with a ratio of the conjugate weak base to conjugate weak acid. All right, so this is my base to acid ratio. If you are wanting to know the exact concentration of conjugate weak acid to conjugate weak base, right? This tells you 3.24 to 1, right? So that could be 3.4 to 1 molar to 1 molar, or it could be 0.003 to 4 molar to 0.0001 molar. Right? You want to get out of that ratio, they got to give you a way out, right? And that's either going to be by giving you one of the concentrations that says this is the ratio, and I had a 0.02 molar solution of base. Well, and then I can figure out what the concentration of the acid would be. Or it could say the total acid and base is going to be like some ionic strength. So they can give you the total of how much base and how much acid you've got, and then you can use that to escape your ratio by substitution. So you substitute that back in. So one of those two ways will let you escape that ratio.